Awesome. I think we are live now and I'm unmuted. So, yes, happy Sunday, everyone. Good morning, good evening, and good afternoon on people joining us from different time zones. Welcome to today's Open Neuromorphic Student Talk. I'm Sundar Raman Rangarajan. I go by Sundar, and it's a pleasure to host this session, Architecting Neuromorphic SoCs with ReRAM and open source tools, alongside my co-host Erastus Stowe. We are thrilled to have Samarth Jain, co-founder of BM Labs, who's joining us from Singapore today for a hands-on deep dive into neuromorphic hardware design. Summer's journey from a student research project and a Nature Communications publication to founding a startup building open source compatible neuromorphic IP is truly inspiring. Over the next hour, you'll get to explore how ReRAM non-volatile memory can be integrated into Caravel platform on SkyWater SKY130 and how open source tool chains like OpenLane 2 are enabling real-world chip design. We'll also hear about the NVM Power-Up Design Contest, where your project could be selected for free fabrication on the upcoming shuttle. So stay tuned if you're looking to turn your designs into silicon. So with that, let's dive right in and welcome Summer to lead us through this fantastic world of neuromorphic SoC design using open source tools.
Hi everyone, I am Samarth Jain, CEO of BM Labs, and thanks Sundar and Erastus for the introduction. Today, as Sundar mentioned, is about turning your brain-inspired compute ideas into a shipping silicon. Our company makes ASIC IPs for neuromorphic applications, and we are very happy to announce that our IPs are now fabricable using Chip Foundry, our partner. So we can fabricate our IP, which we are going to show on any MPW shuttles. This means that you can seamlessly integrate our compute and memory IPs into your SoC projects and tape out using MPW tape outs. So today we are going to introduce BM Labs as your go-to IP provider for brain-inspired computing. And we are going to start with an introduction to BM Labs, our crossbar IPs, or we call it as X IPs overview. We will also show you how you can integrate our IPs using open source tools like CocoaDB and OpenLane. Whether you are a startup or a university student, and you can take participation in our NVM innovation context called as NVM Power-Up. So where in which you can get chance to have your IP fabricated for free. At the end of this webinar, we will be showing you a roadmap for our future IPs, the benchmarking, some sample IC design projects, and we will have Q&A. So at BM Labs, which stands for Beyond More Labs, we build neuromorphic semiconductor IPs, which are energy efficient based on ReRAM crossbar accelerators, plus they have mixed signal peripherals. Our mission is to bring brain inspired compute to edge devices via our crossbar series of IPs. What makes us different is our IPs are compute and memory compatible, and they are clean SoC designs, very easy to integrate with open source flow. Brain, as you know, is an event driven, ultra low power organ, and our IPs are inspired from its architecture. GPUs are great for dense throughput applications, but are less ideal for always on task, right? So our IPs takes the brain like efficiency into silicon building blocks as the fundamental of all the ideation. So over here, you can see that we mentioned about ReRAM. Some of the people might not be aware of what is ReRAM. So ReRAM stands for a resistive RAM, and it, as shown in the bottom right graph, it's a comparison of a ReRAM with a biological synapse. So in our synapse, we have ions moving, making plasticity and things like that. That's how we remember stuff, right? So the ReRAM on the right hand side is similar. is just instead of ions like calcium which are in bodies, we have metal ions, which are maybe titanium or something like that, and they migrate as we apply potential, and they can form a filament or they can break the filament, and that's how our IPs are fundamentally a neuromorphic IP at a cell level. So if we look at from IC design perspective, our design is called as X1 32 cross 32, which simply means that we have a 32 cross 32 resistive RAM arranged in a crossbar fashion, right? So you can see on the right hand side, it's a picture showing uh, the full SoC design, and the white area is where your design goes. So you can see our IP, which is consisting of a crossbar array. It has some peripherals, it has digital control system in it, right? Peripherals like ADC and so on. So the crossbar in the center is a one transistor, one resistor, 32 cross 32 ReRAM arrangement. So the ReRAM or this IP has an analog behavior. That's why we have a digital bus, which is called as Wishbone, available in this IP, which you can directly hook up with open source RISC-V, available in something called as Caravel, which I'll be explaining later, right? So you can just take our IP, connect the Wishbone slave available in the IP, which gives you a digital interface, hook it up with the Wishbone master bus in the RISC-V, which is open source, and then you have a full communication and a working SoC available, right? So our IPs can be taped out in any of the shuttles available on our partner MPW, and the next shuttle is going to be on November 11th. And one of the design which will be submitted in our competition is also going to get a free chance to be taped out on the shuttle. So I mentioned a lot about open source tools, right, and how our IP is compatible with open source tools. So there are two main tools which we are going to look into today. First is the OpenLane, which is a tool allows you to simulate your IP and do the full RTL verification, sign off till the GDS. And after that, once your GDS is ready, it goes to our partner, which sends to the factory, foundry. They do the packaging, manufacturing for you, and in the end, you get a development board with your chip inside it, which is as simple as using Arduino, right? The other open source tool which we are mentioning over is the Caravel. Essentially, a Caravel is a design which has a RISC-V processor, Pico RV RISC-V processor. It's a very simple RISC-V processor. And the Caravel has pad frames like analog pads, digital pads, which you can just connect your design to and then send it to our MPW runs and get a fabricated chip with it. So there are open source discussion community for OpenLane as mentioned at the bottom, and for the Caravel as well. So if you have any questions, you can read the documentation, you can communicate on the community. So first we will be showing you a demo after this slide. So the Neuromorphic X1 is a NVM IP, right? And it works similar to EEPROM, but it is embedded, right? So it's kind of very useful for low latency tasks because inside the chip, right? And it's a non-volatile, so you can just store your data and recover even the power is down, right? So I'll be showing you a very simple demo of how you can at least take your behavior model of your IP or any idea you have in Python or something like that and do a timing analysis which is required for a ASIC flow. Yeah. So in this demo, we are just going to go to our GitHub repo, which you can just follow it. And this is a GitHub repo available. It's an example repo. right? With our simple IP, there are steps. So if you want to download the IP, you can just pip install this command, and it's just going to fetch the IP, the data sheets, and the behavior level model directly into your computer. So let me try to paste it into the terminal. Yeah, so the IP is already there inside this PC. So I just showed you the step. And the next step is going to be, uh, let me see. Yeah, so the first step was installing the IP manager. Second is going to install the specific IP from the server. Oops, there's some error. Let me check that. Yeah, so we're just trying to install the IP from the IP manager. Yeah, so this is installing the IP. It's fetching from the server. And now we are going to see what's there inside the folder. So there should be a Neuromorphic X1 folder, which has the HDL behavior level IPs, the left files, the GDS file, whatever you require to do a tape out. So now we are going to simulate this, the timing diagrams, using the open source tool called as CocoTB. So it's a tool where it's built on Python, and you can do RTL verifications, right? So we are just going to run a test bench using this, and then later on show you how the test bench was written. So just to run the default test bench, you just need to write this command, which is just going to do a read operation to the IP, write operation to the IP, and it's going to very similar to a EEPROM. So this is the simulation running. So you can see it's starting ReRAM test. So that is the TB which we have written in the demo folder. Yeah, so it's just printing some command which we have written in the demo, and we'll be going through it now. But you can see it has successfully completed the simulation, the timing simulation. And let's try to see the Verilog files. So it's under this RAM underscore world. So there are two files. One is the firmware file. So as if you have an control like Arduino, you will write some firmware, right, to interact with your accelerator. So this is the firmware file written in C. So you can just see that I'm trying to write an address and the data to the IP. So the address is in hex, which is 3 followed by zeros in C, and the data I want to write it to the IP. You can find more details about how these registers are filled on the GitHub page, the memory mapping and things like that, right? You can use this example. And in this, I'm just trying to write on the wishbone slave, which is on the 3000, 3 followed by zeros, and C address is of the slave of the IP. And we're trying to write data into the IP. And these are just timestamps. Like when I'm trying to start the writing to the IP, I will just put a print statement when the IP is writing to the uh, NVM, it is showing as a processing. And these all things were printed on the background screen when we ran the simulation. So after you have run this firmware, you can see the timing diagrams as well. So you can see the timing diagram of each and everything happening inside the IP, which you will require to design a chip. Yeah, so to understand these names and things like that, you will have to read the data sheet in the doc folder of this IP, right? So you can just plot these signals. These are wishbone signals, because I mentioned the IP has a digital interface with the Caravel, which is a RISC-V processor using wishbone. So we are trying to see the wishbone signals here. So first we are going to see the write operation of the wishbone. So you can see over here, we were writing to the three followed by zeros and C address, which is a wishbone slave address. And there was some data which we were trying to write to the NVM IP. So that's this data shown over here in the data bus of the wishbone. So let me try to show you that. Yeah, so this was the data we were trying to write. You will have to read the memory map because this data bus corresponds to the cell address in the crossbar array you want to write, right? So I mentioned the 32 cross 32 crossbar array. That's how we have arranged these memory strip cells. So they have an x coordinate and a y coordinate of each cell. So this data W data register has the x coordinate, y coordinate of the cell, followed by what value you want to write to the synapse. So these are just the memory mapping. I'm trying to show that the row address is the following bits. That is over here, 29 to 25 bits are the row address. So the XY coordinate, which I mentioned, the 32 cross 32 crossbar array.
Which so, for those of us who don't understand, what is the purpose of the crossbar bar array?
So the crossbar in the X1 IP, later I will show we have other IPs as well. But in the neuromorphic X1 IP, crossbar is maybe like a SRAM, right? SRAM, you have a 1 kilobit of SRAM arranged in kind of parallel ladder kind of way. So the crossbar is just a way to access each cell. It's like a chessboard. So for a chessboard to arrange to access one cell in a chessboard, you need to have a XY coordinate, right? And then I want to program that memory because the memory stir is a memory element. So then I will put a data into that. For example, I want to store 1 into it or 0 into it. So that will be the data component. So once I write that command into the right bus, x coordinate, y coordinate in the data, it will store that data. Then later on, I can come and do the read cycle for it. So the data will be still there even if the power is gone because it's a non-volatile memory. It's not like SRAM where if you turn it off, it goes away, right?
Yeah.
Yeah, so I think Sundar, that was about the demo. There are files inside this as well where you can see the whole behavior level code of this IP, which is just depicted by this image over here. So the IP has uh, one page access. It has an input FIFO where you can just load the XY coordinates and the data you want to program the crossbar to in a queue, and then the IP will take care of writing that data, right? It will take its own sweet time to write the data inside. And then when you want to read, it has output buffer. So you can just give it an instruction that, okay, I want to read these all cells. Can you give me the data out? So you can fill the FIFO and it'll give you the data out. So people can go to this GitHub repo and explore more.
Okay. Just a quick question. So we have
Yeah.
a question from the audience on YouTube. So he asked, like, he's also curious to learn more about OpenLane and LibreLane. Are there software or hardware bits? How were they made? The question is
Yeah.
just coming up on the screen here. Yep.
So you can find documentation for it, open source. So there are full documentation of how this open lane is made. Plus, if you want to interact and chat to the community, you can just go to this community link and you can chat with people over there. So they are actively developing open lane, or if you want to interface some IPs like ours, we are also actively involved helping people out to solve some doubts they have, right? So it's a very big community for open lane. It's always very active. Yeah. So the whole code is also available. You can just type open lane on Google and you can find the whole documentation about it.
Got it. Got it.
Same with the Caravel as well. So Caravel also is a harness which consists of all the analog pads It's a very complicated stuff, right? So it makes life easy. So we just have to focus on your design. Maybe it can be a neuromorphic IP with ours combined with your own design, and then just follow the Caravel flow, which I'll be showing you a demo later. So after you have done simulating your stuff, you can just use the Caravel flow, and then if you have some doubts, you can join these chats. People can help you out, right? So it'll help you integrate to the final chip which goes to the foundry.
Sure. And another follow-up question is Caravel an open architecture or open source as well? Like,
Yes.
okay,
Yes, both are open source. So our IP is compatible with open source tools, EDA tools, which help the startups or the researchers not to worry about hefty fees by EDA tools. They're quite expensive, so they can do a prototype using this quite fast.
okay,
Wait,
So
so yeah,
yeah, yes, yes.
so let's just assume that someone wants to get into developing neuromorphic hardware. They really have no prior experience apart from basic and fundamental research. Like, how do you get into developing neuromorphic hardware?
Yeah. So I think what you would need is just a simple Verilog writing experience. And if you don't have also, I think you can use GPT for sure. Once you have your Verilog code ready, just use CocoaDB to verify your timing, right? So just write a Python behavior model of your IP, right? Or write a block diagram. Okay, first you can start with the block diagram. Give it to GPT, write a Python behavior model, convert that, and then check that Python behavior model first whether it does what you need mathematically and logically. Then maybe convert into a Verilog, simple Verilog, behavior level Verilog. Simulate that behavior level Verilog, which is just maybe mostly represented by C programming or Python programming, right? It can be, there is no RTL level, there is no transistor or IC design in behavior level. It's just maths. So just write your behavior level Verilog, validate it using CocoaDB, which I just showed you, right? Use that tool to verify whether your design makes sense. Once your behavior model is ready, use it to convert into Verilog, right? And then use the open lane to make sure that the Verilog can be manufactured. So you have to go through some iteration using Verilog and the open lane, right? Go through some iteration. There can be some timing analysis or something which is very not that difficult for a simple design, right? You can start with that. Once it is done, you can use open lane to do full hardware level design for you. It's all automated. The layout is all automated, right? During this process, you can also use the behavior model of our IP and integrate with your behavior model. Again, simulate on CocoaDB. Use OpenLane to do all the automatic place and route, right? Use the C program, which I just showed you with the Caravel, like an Arduino C program. Check on the behavior level whether it's working fine. Use the OpenLane to finally submit it to the factory, right? So it's very easy if you are a digital designer. It might be a little tricky if you want to do in analog domain, right? That's why we provide a digital interface to our IP so that's very easy for a first time beginner to use these IPs because the digital flow is very much automated right now. Right. So if somebody wants to like do a simple tape out, right? So we have a competition called as NVM Power-Up. So I think somebody asked, what is Verilog? Verilog is a language used to program chips, right? It's like a C program. C program, you can write a behavior level logic for your idea, right? And then convert into Verilog because Verilog can be understood by all these open source tools, right? So just write a behavior level, ask GPT, or maybe if you have some friends who can help you convert into Verilog and then insert into this open lane flow, and then it'll give you a hardware which is required to do tape outs. And for trying, we have a competition for students right now. This is in collaboration with our embedded and tape out partner, Chip Foundry. So in this competition, No matter your background, you can first start with your proposal, which is a behavior level proposal. Just go to this link which I'm showing over here in the blue color, and then you can read the description. You can write your schematic, the idea you want to do it, right? Start with that, and then a simple behavior level which is described on this link. Once that is done, we can move forward to the next step, which is the Verilog step, right? So in this, we will be showing you some examples of how people have submitted. It's all open source. So you can see how other participants are submitting their projects, right? And then the final winner will be getting a free SoC, which will be fully packaged and in a PCB, which you can just hook it up to your computer and start experimenting with it.
So, yeah.
Awesome. And
Um,
we also have another question. Um, Sorry, Estes. We just have a question on the chat. Can you please briefly discuss about the crossbar arrays? How can I design a memristor crossbar?
Yeah. So in the IP we provide, we already designed the crossbar, right? But if you want to design on your own, our partners do provide the memristor. So memristor is just like a capacitor. The physical structure is exactly same like a capacitor, but it is like a resistor, variable resistor. Okay, so the physical structure is capacitive, but the property is resistive, and you arrange all this with a selector, which is one transistor. Because if you have a crossbar and you want to select maybe a cell 0 comma 0, first you will turn on the transistor which is in series with that resistor, and then you can access that cell so that the other cells don't cross talk with each other, right? So you can arrange a 1T 1R crossbar array, and then you can design the peripheral around it. It might be a bit tricky, it can take some time, so that's why our IP provides the crossbar with the peripheral and a digital interface. Because as I mentioned, in the analog design becomes bit advanced compared to the digital design, right? So it becomes little difficult. But if you want to read more about the crossbar, you can chat with us on the open source community. The We are actively available on OpenLane community or Caravel community, right? There are some communities for ReRAM as well, how to design it. So you can join that and you can get more inputs on that.
yeah, so this is a question that some people might be wondering. So like this neuromorphic X1 is based on biological neurons, right? Like could you describe the relationship between like membranes and like neurons?
So our neurons are actually membristors. So fundamentally, the definitions, there are, I think, fundamental devices. One is resistor, one is inductor, one is capacitor, and the fourth is memristor. So under memristor, our neurons also are categorized as membristors. Even ReRAMs, resistive RAMs, are also categorized as membristors. So the fundamental definition of memristor is that uh, it has ions moving, okay, instead of resistive properties. It has physical ions moving from one place to other place, which is a synapse, right, in electric field. And it has a memory effect, right? It is depending on the previous input, so it's a memory device, same as our neurons. So they all are categorized under a common umbrella called as memristor.
So like how does like membranes remember? Like can you talk a little bit about that?
Yeah. So as I showed on this image, if my slide is available, you can see on the left side how we as a human store is that we move maybe calcium ions or some, there are a lot of ions, right, which are stimulated by neurons electrical firing, and they are moving across the synaptic gap, and then they connect with the other end and work as like a lock and key mechanism, and then they store some states in our body. Similarly in in ReRAMs, resistive RAMs, the ions, in our case the metal ions can be Ti or something like that, they migrate and they form filaments. The filaments can be thick, the filaments can be thin, right? So based on the thickness, the resistance of these filaments are determined. So the resistance is the weights, is how we store the memory. We can control the resistive states of these elements. Yeah.
So it seems like there is a lot of neuroscience involved in understanding memory this way. How much neuroscience do you need to actually get into this field? Essentially?
Actually, we don't need, I mean, if you have to design a new neuron at a cell level, you might need, but at a design level, it's just like a variable resistor,
Okay.
right? So you don't need much complicated modeling for it. It might get complicated when we are designing the IP. We have, there are a lot of open source emulators or uh, codes available to emulate these devices, right? So you can get those things. It involves, if you see the fundamental equations, they are just moving the ions, but at a bird eye view, they are just resistive states, and there are a lot of resistive states. It's analog. It can be, for example, 5 kilo ohms, 10 kilo ohms, 100 kilo ohms. So as a designer perspective, it can be a variable resistor. So, as I mentioned previously, the COCO TB is for the behavior level simulation. You have your idea in block diagram, you convert into Python, then you convert into behavior level Verilog, which is just addition, subtraction, multiplier kind of operations. And then you do a simulation using COCO TB on a behavior level, just a timing pulses. After that, you need to check your design whether it is manufacturable or not, and the tool for that is called as OpenLane. So we have a demo for the OpenLane in which we'll be showing you, you put your Verilog code and you get your final GDS, which is the one which goes to the factory for manufacturing. So Sundar, can we play the video? I think we would have to also forward the video a bit, but yeah, if you go to a competition page, you can get an example at the bottom, which will give you an example of how to run this open lane flow with a sample, just our IP, and placing it into the Caravel harness and sending and doing the full open lane flow. So we just did the first two steps, which was running the simulation using CocoTB, right? So now we will be doing the step for open lane. So let's just open a terminal over here. So this was the IP which we installed previously. It has the HDL and all sort of behavior model which we use for CocoTB, right? So now we are going to, so once we have verified the IP, we are going to generate the GDS. So to generate the GDS, we have to go to the open lane folder. One second, let me check once. So these are some of the files which we have to initialize. There are more videos on the same competition link. You can see how to initialize like the default state, default state of the pads, right? We have a Caravel SoC, so they have some default configurations. So you can just set it or you can just leave it. It has some default configuration as well. But if you want to change on your own, you can change that. So once that you have done that, you can run this make command and it will start taking your Verilog code, which you generated using CocoTB, and do all the process for you from taking your Verilog, placing it into an actual hardware, doing the timing analysis, whether your system can meet the timing constraints, right? Because there's some timing constraint provided by the Caravel harness, because you're using wishbone interface, so you need to meet some timings. It will also do LVS checks, which is layout versus schematic. because you need to check whether all the pins are connected, there's no floating nets, things like that. So I think right now it might be doing routing. Yeah, so you can see it's on the step 46, which is detailed routing, and this tool will generate reports for each step as well. So later on, once we finish this, uh, we can see at every step there's a report generated, because you might fail on one of these steps and then you have to debug. So you have to go and read the report and then you have to debug. So Sundar, maybe we can try to forward this a bit, because it's a detailed routing, right? So it's going to take some time. We try to forward it a bit. Yeah, so it's trying to like place your design, check for violations, things like that. Yeah, so if you follow the standard Caravel designs, and there's some sample designs available, then I think you should be good to go. So now it's trying to use the open source tool called as Magic. It does the physical layout, right? And it generates the left file, GDS files. It uses K layout for checking the design rules. There are some rules by the foundry. It has to check whether the cells are not too close to each other, things like that. So there's some design rule which has to be followed. So once your process is done, so you can see the process has been finished and we have all the checks clear, which is antenna clear, LVS clear, and design clear. So finally we can see the GDS which goes to the foundry, the factory, right? So this tool will generate the file which goes to the factory, which you can just submit to the MPW runs via partners, and it can just go to the factory. So we'll try to import that GDS, which is generated by OpenLane, in the K layout to view it. So it should be under OpenLane folder. Runs. Yeah, you can go under runs. You can check the latest run. Yeah, so I mentioned it will generate report for every step. So because our design, the sample design which we have on the Git passes all the test, so we can just see the final reports. It generates all sort of files. GDS is the one which we require. So we can just import this file and view our design of the IP. Yeah. So you can see this is the 10 mm square area which is provided in our NVM competition, and the IP is on the bottom left, connected to the wires, which I think I will highlight using pink. So the pink wires are the one going to the bottom, which is connected to the RISC-V processor. So it's all automatically done if you follow the example. And the RISC-V processor comes just bottom of this. So once you give your, once you do this checks, which are on your local system, right? You have to submit this to the, for the foundry checks, which is done by a partner, which will integrate the Caravel SoC with your design, right? So it will integrate with the RISC-V, but these are the RISC-V wishbone pins. So let's try to trace one of the wishbone pin, like a data pin, which I showed in the simulation, right? So let's
Before
try
we,
to track that pin.
before we do that, can we discuss the RISC-V? What is its purpose in this design?
So the RISC-V is the open source Pico RV. So there are a lot of flavors of RISC-V, right? RISC-V is a CPU. It's like you have Intel CPU or ARM CPU. RISC-V is a CPU.
Yeah.
And we are using an open source CPU called as Pico RV. It's a flavor of RISC-V. You can find the documentation about it, right? So it's a simple CPU with wishbone interface, which you can connect. Wishbone is a bus. It's like maybe CAN, AXI. You would have heard these names. So wishbone is like a bus, very simple bus, which you can use to communicate digitally with your IPs. So there's a master in the RISC-V already built in for the wishbone, and there is a slave already built in the NVM IP which we provide. So you can directly interact with the memory mapping available in the datasheet. Yeah, so let's just trace one wire till the end of the SoC. I mean, to the neuromorphic IP. So the scale layout is like a very nice tool. I think it's free. So it's a free tool. You can just use it. Magic is also a tool which you can use for similar purpose. Same open source and free. So you can use these tools to access. You don't need any proprietary tools for the whole flow. Yeah. So as we follow this wire, we can follow the data line, and you can see all this routing has been done automatically by OpenLane, right? So you don't have to do any routing on your own. And this is the boundary of our IP. So all the pink wires are going and connecting to the IP. Yeah. So I think Sundar, this is all for this demo. We can go to the slides. Yeah, Sundar, I think you have to stage the slides.
Yeah, I think it's there. Can you see it?
Not yet.
I can see the neuromorphic IP roadmap. Give me a second. Erastus, are you able to see the slides?
Yes. Now it's
Yeah, it's back. Okay, thank you. So whatever we have described right now is about neuromorphic X1, which is a crossbar 1 IP. The X1 IP is a 32 cross 32 NVM IP, non-volatile memory. It's very similar to EPROMs, which is very might be familiar. You guys might be familiar with. And it's the difference is that it is an embedded IP. It's available inside the chip, so it's like SRAM. You can keep it near your accelerators. It's quite good for ultra low latency applications because it's inside the chip. You can have a deterministic latency with it, right? It's not outside where there can be a lot of other latencies. So it's very good for sensors, industry 4.0, and things like that. We are also going to release a IP called as neuromorphic X2, which is a compute and memory IP, which is essentially a MAC accelerator or a dot product accelerator. So it can run AI workloads like mobile net or any CNNs, things like that, right? So the major difference between X1 and X2 is that X1 is a storage memory IP, non-volatile, and X2 is a storage with a compute inbuilt, right? Because as I mentioned, the ReRAMs are just variable registers. Even Aristotles asked this question, right? So you can use Ohm's law to add current and subtract current, right? And you can use the ReRAM as a weight, the resistance as the weight. So you can use Ohm's law for multiplication. V is equal to IR, or conductance. You can write in that way. So you can do the multiplication operation, and you can do accumulation using current Kirchhoff law. So essentially this crossbar array, we arrange it in a manner that it can do the dot product, which is multiplication and accumulation both. So that is the X2 series of our IP, which will be releasing in the next year, right? We will be also releasing a behavior model and the compiler for it very soon, and it'll be open source, right? So we'll keep everybody updated on that.
so if we can talk a little bit about the X2, can you just talk
Hmm.
a little bit about computing memory?
Yeah, so compute in memory, as the word says, that it is doing compute inside the memory, right? So the existing hardware, maybe you can take a very popular example of NVIDIA A100 or H100, right? They have a dot product accelerator or a CUDA unit, which they can call it as, right? And they have a L1 cache, which is a SRAM, but it's very small. So majority of their data is stored in HBMs or a DRAM, right? So they have to do back and forth every time to fetch the data, and the bottleneck is the bandwidth because they have limited amount of buses, and then to do compute is in the GPUs, but the data is stored inside the HBMs, right? So there's a lot of memory hierarchy. Using X2, you can at least combine the L1 and the dot product acceleration into one unit. It might not be able to replace HBMs for now because the density is not that big. That's where we have a X3 IP in future, but you can at least avoid the L1 data latency or maybe L2 as well, and combine everything into one IP, which is this compute in memory IP. So it does the dot product of the matrices, which is a fundamental building block of any CNN or any LLMs, right? So you can do everything inside the memory cells. You can store the weights, and then you can do the dot product also at the same place.
So this seems like really awesome and it seems really efficient. How efficient is it compared to the traditional approach of fetching from memory?
Yeah, so I was getting to that for the benchmark page,
Okay.
but maybe we can straight away go to it, right? So on this page, oh sorry, one second, I'm trying to make the screen big. Yeah. So on this page, you can see our behavior model of RX2 and the tape out which we have done right now. It's under manufacturing. So using that data, we are comparing our chips. For example, this is for MobileNet V2, a small AI model. We are comparing with various NVIDIA chips like Nano, it can be Jetson, Orion, right? Because they fall in this category of maybe 20-watt power chips, right? So we can see that they are so the topmost graph shows the latency versus throughput, which is very known metrics for any CNN or classification kind of models. So for MobileNet V2, we can see it has a quite impressive latency and throughput, even though this is simulated on 28 nanometers technology, whereas the other competitors are below 5 nanometers. So that's where we started. This technology is cheaper because you can get the same performance at higher nodes. Is just the reason because the SRAM which you make might be at least 6 cells. You need at least 6 cells. But whereas this one cell, this 1T, 1R can do compute and store at the same place. So you save space, right? And that's why you can afford a higher technology node to achieve the same performance and cuts down your cost. And our technology is CMOS compatible, so you don't need any fancy integration. It's all on the CMOS fabs. So our chips are fabricated on SkyWater. It's a US based fab right now. It's completely CMOS compatible. As I mentioned, like a capacitor, right? So it doesn't need special process. I have few more graphs on the bottom. So if you want to project this at a technology node competing with say 12 nanometers, right? Then it is getting better than even Jetson Orion kind of chips, right? So at the same cost, it gives you a better performance.
Well, what about the energy efficiency? It seems like if you're doing memory and computer at the same time, it must be more expensive, right, in energy. So
Yeah.
how is that?
Yeah, so I think we have some parameters. I'm not shown over here, but if you go to our website, which is shown on the bottom, we have run these models with our compiler, open source compilers, and our models for models from CNN up to LLMs. And we have publications as well. So you can go to our benchmarking page and there are citations. You can check how we simulated, and we will be soon releasing our compiler and the tool as well. So we use open source tool. The compilers are made by us, but the tool for arranging these AI models is an open source tool. Yeah, it's all cited on this page.
So, and I think like we also have another question from the chat. That would be for programming the chip itself. Does BM Labs have a tool chain to compile firmware or to run a tiny ML model?
Yes. So the best part of this is that for the NVM computation for X1, you don't need any special tool chain because we use a RISC-V processor, and it's just hardware connected using a wishbone bus. So all the compilation, all the RISC-V firmware, you can just compile it using GCC or RISC-V compilers, right? All open source. And the X2, we are going to launch the open source compiler for it, which is not yet launched, right? So that will give you a provision to deploy CNNs and LLMs on these chips.
Got it.
Yeah. So as I was talking about, Aristus asked that what is in-memory compute and how does it benefit? It is benefiting because we are trying to cut down the access time to L1 and L2 at least, right? We can match the density of L1 already, and we're trying to match the density of L2. So you don't kind of need these memories, it's already there in your core. So it saves a lot of energy in transporting the data back and forth, right? Even L1s are quite complicated. They have multi ports to make them high speed. So it's very convenient to have everything inside the same memory. Whereas if you want to run maybe things like Llama, right? So if you see our benchmarking page, we have done benchmarking up to Llama. How do we do that? We have explained that as well in the papers, but there's a short description over here that we used multiple of X2s, right? Connect them with buses interface and have a global L2 buffer. And we use the open source tool to map these Llama models on these chips and do the full benchmarking of these using the actual workloads, right? So this IP is called as X3, which is a work in progress. We are developing special buses for this to connect various PE, which are processing element, uh, which will help us to connect all these processing elements, which are X2 IPs, efficiently and do the in-memory computing for bigger models. Because for Llama kind of models, you need multiple cores. If you check out A100 or H100, they have thousands of cores, CUDA cores, just to do that compute. Going to one of our final slides. So I mentioned about NVM power of competition. So this competition was launched before. The 17th was the deadline for the proposal, which is just a GitHub page with a README file. But we are still reviewing the projects, and we will be accepting projects up to 20th or 21st. So please do submit your projects, and you can get some sample projects of existing participant which are open source on the bottom link. You can see how people are using these IPs for analog sensor interface. Like some people have used it for heartbeat monitoring and saving some sensitive data which needs to be there even if the power is gone. So they are using an heartbeat sensor, making an analog front end and connecting to the neuromorphic IP for direct low latency saving of data, right? So there are projects for that. Some people are using it for applications where, like for example, Mars rover kind of thing, long hibernation, right? There's no power for a long time, so your data has to be saved for long duration. So some people have proposed projects using that, and they will be taping out in the November shuttle. Few people have used it for application like pacemaker, because if you Google it, ReRAM is radiation hardened. Maybe the Caravel SoC might not be radiation hardened, but our IP fundamentally can be qualified for radiation hardened after a few iterations. The reason being is that it doesn't work on charge. Charge migration using tunneling, which is the MOSFETs, how they work. It actually works on physical ions moving. So it's a solid filament, like a metal filament, right? So it is it can take more radiation things and higher temperature and things like that. So that's why people are using it for applications, medical applications. Some people have proposed for pacemaker. They might not be making pacemaker, but they are working on a small part of it. So all the projects can be found on this, and they are developing these works. So you can take inspiration from these GitHub projects, IPs, and how to integrate our IP to your designs.
Um, Thanks, Ahmad. And then I think we have just one question from the chat. Is it possible to implement neuromorphic computational filters or kernels on FPGA?
Yes. So what you can do is you can take our behavior model and you can implement that Verilog into an FPGA, right? So the behavior model is a Python based. You convert into Verilog. That Verilog can be synthesized by OpenLane for chip manufacturing, or you can use an FPGA, Xilinx synthesizer, things like that, and implement that on FPGA. Yeah.
Awesome. Yeah, that was the only question. And I'm sorry, we have another question. How many bits per ReRAM cell can hold, or it depends on the firmware?
So that's a very good question. The neuromorphic X1 IP, each cell is single bit, and the X2 will have more bits. It depends on the compiler and the firmware version you deploy on the IP. Yeah.
Got it. Okay.
But the cells, the VRAM cells we use, we provide the data to our customers. At least 4 bit of data for each cell can be programmed. Yeah. So we have tested about 50 chips. We have done our own tape outs. We have tested the chips, and we have data for the 50 chips, right? So once we have we have a customer. If they ask us for these testing data like endurance, retention, these are things which are required for a memory design. How many bits, as you asked, so that all data is available in that data sheet.
Okay. Got it. Yeah, those are the questions online. Okay. Is that your last slide, Samarth, or do you have something else to share? Oh, okay.
Yeah. So apart from the competition, if people want, like if there's a startup, if they want to use this IP for a commercial purpose rather than a research project, they can directly reach out to us or the chip foundry, and they can use the same flow, because some people don't want to open source their designs once it has like matured, or some part of that structure they want to open source. So if you want to have a proprietary run, you can just have our one-time prototyping license, and you can prototype it on the SkyWater run. Yeah.
Awesome. Interesting. Rastus, do you have anything to add?
Yeah, I mean, this has really been
Yeah,
informative.
it's a great learning experience, and it was fun learning about things. And
I'm very big into process of design, so this is something that I really needed to see. And it's very possible that with some fundamental knowledge, you can really start making something that actually works. You can see it in the time, so that's really great.
Yeah,
awesome.
it's just, I mean, the process is simple, super easy, uh, and it's all open source, so it doesn't hinder any researcher or student to bring their ideas from a behavior level till the manufacturing, right? I hope that the full flow was like quite accessible, that you can just sit overnight and get everything done using GitHub, GPT, kind of things.
I mean, something I always thought was that you needed some extensive prior knowledge of like computational neuroscience or some electrical engineering, but it seems like you really don't, right? It seems like there's some basic knowledge, you can get something working. So that's really great to know. Yeah, and it seems like the documentation out there with these open source tools that can help really help anyone like you get started.
Oh, go ahead.
Yeah. And the best thing is like there are a lot of examples provided, like a reference examples on this GitHub. So if you want something like you want to get started, I would recommend everybody to just look at these examples and see them evolve. The teams are working quite hard for the competition, and they have finished the ideation, and now they are making the full open lane flow. So you might be able to use these designs to make even more exciting systems, right? And you don't have to go into details of how to design detailed IP, because there are existing frames or templates available. Sundar, you were saying something? Sorry, I cut you off.
We just have like one basic question from the audience. Can we learn about neuromorphic computing after bachelor's, or would this make sense only to PhDs?
I
I
do.
think you can just you can just try to put your design on the competition, and then you will get your answer. If it gets taped out and you get your own SoC chip, you might not need PhD for that.
That was a good plug-in.
Yeah.
So,
But
uh,
yeah, if you want to go into device fundamental, you might need PhD. But if you want to design an ASIC using it, I think masters is a good enough platform for it.
right. Interesting.
Also, if you have no knowledge of computational neuroscience, there is a course out there is called Neurodynamics that is professor from Germany. It is a very extensive course that he explains all the mathematical models behind like all the neuroscience models. He explains all of that. He gives you the math behind all of it as well, and how you can actually use them to actually build like models like the LIF, Leaky Integrated Fire Neural Model. And it's like a really good starting point. If you have no idea what computational neuroscience is, you should really look
Yeah,
into
I
it.
think Erastus, can you come closer to your mic? I think somebody texted they are not able to hear you. Maybe. Yeah.
Is this better?
Okay. Yeah, it's better. Thank you.
Yes. So I was saying that if you are interested in neuromorphic computing, a great place to start is a course online. It's called Neuronal Dynamics. It's also a book as well that you can get. And the course goes through the fundamentals of neurons and things like the leaky integrated firing neural models and all the other neural models out there. Explains the math behind it and how you can actually implement these models. It's a very good course, and I highly recommend it. I actually used the course to get the basic understanding of neuromorphic computing, or computational neuroscience, to say. Yeah, and you need a little bit of computer science and electrical engineering, which on the electrical engineering side, I recommend a book, The Elements of Computing Systems, which basically
Yes.
teaches you and it's going to you how to develop the Neumann architectures. And I think like with that understanding, you can be able to start understanding like neuromorphic features. I find this to be very useful.
Yeah, I think Erastus mentioned very good keywords, which I think I have not mentioned. One was the leaky integration model, which is quite popular. It's just like we keep firing pulses to the neuron, and at a certain threshold, it accumulates and then gives an output, right? So it can be acting like a non-linear function. So these are like few models which you can use to mimic a neuron, right? Uh, but I believe that there are more models which can be explored apart from leak integration. Leak integration is quite good for SNNs.
Yeah.
It's a kind of neuromorphic computing uh, which involves on this leaky integration firing kind of modeling. You can also use resistive memory, as we showed, like a memory element, right? So the neurons can be made of multiple things. It can be a memory element coupled with a nonlinear activation function. So this ReRAM works as a memory element in the neuron, right? And you can attach your own nonlinear activation function with this ReRAM to make your more realistic models with it.
Actually, so that was something I was going to ask you. Is like, how do you integrate members of devices with like leaking integrated firing neural models, right? And I was actually going to ask if the the learning, the on-device learning, if it's based on something like the ADX model.
Yeah, so I think For leaky integration, how you can do in our IP is that our sense amplifiers are capacitive in nature. So you can do integration using capacitor, and you can use the memory element from the resistor ReRAM that we already incorporate in our X2 IP, right? So from a designer perspective, from a digital designer perspective, you just have to give the command that I want this kind of behavior. Using the behavior model you can check, but inside the IP we use a capacitor to integrate and use the resistive RAM as a memory, so that forms a complete leaky integration kind of neuron.
So you are implementing a sort of really integrated firing normal between the IPs. I actually was that was something I was really curious about. But I didn't really know that that was something you're actually doing.
Yeah, that's a very common way people do, like they couple with register with capacitor to emulate this kind of behavior.
So, like, which kind of really integrated firing neural models are you using? Are you using like a linear, nonlinear, exponential, or adaptive exponential?
So we use a normal thresholding, which is a linear one,
Yeah.
right? So the IP has that for now. But you can do the non-linearity in the digital domain. Like you can use lookup tables, things like that, or you can make your own digital IP and connect it with our IP and do the non-linearity part using lookup table in your digital IP and take the data from like the linear behavior or the weight behavior from the neuromorphic X1 IP. Yeah. So that's the beauty. Like we give you the access to the IP with the pads, I mean, inbuilt pads. So you can directly hook up your Verilog design, which you generated using OpenLane for the non-linearity part or other kind of projects you want to do.
That's amazing.
So I think Samarth, we have like a few questions from the audience here. One is like, I'm curious if there's any need to do ReRAM design verification before tape out, or generally functionality is only confirmed after the test chip is received.
Yeah, so actually, the ReRAM is a very stochastic device. So when we give our IP, we do the device level testing at our level, and we make a behavior model so that it's uniform for the user to just do the behavior level functionality test, right? But if you make your own ReRAM cell, you would have to like do a statistical study of all the cell across the array, and yeah, so you have to do device level and the functionality level both.
Got it. So we just have two more questions, and interest of time, could you like keep your the response like a brief response? I think the first question is, sorry if this is repetitive, but could you over the benchmark tests you did with the X1, how did you perform them, and how capable is the IP in running tiny ML models?
Yes, so we used a simulator called as Mestro. It's a open source simulator. We combine it with our own compilers, and we show the performance is as good as stated in Mestro. We also published a paper showing running from to tiny ML, like you can take like mobile net v2 or things like that, small models we have provided. It's all run on Mestro, and the literature is available, right? We have cited them. We ran bigger models, not tiny ML. We ran LLMs, and we published a paper on that, which is already cited on the benchmarking page. So that would be interesting to know, because tiny ML, you might not be able to see the energy benefit, but when you scale it to the extreme level, then it becomes very clear that there is a difference,
Got it.
right?
So I think like one last question is, do we have full flow for open source tools?
Yeah, so for simulation, you can use CocoaTB for behavior level simulation, open source. For taping out your design from Verilog to the factory is OpenLane. It's also open source, right? So that's all you need.
Awesome. Yeah, I think on both the live chats, those are the questions from the audience. Erastus, do you have something else?
Nothing else.
Sure. Awesome. Yeah. So let's wrap up this session. Thank you so much, Summer, and thank you everyone for joining today's session on architecting neuromorphic socks with VRAM and open source tools. I would really like to extend a special thanks to Samarth Jain. I know it's middle of the night for him in Singapore, for walking us through the intricacies of open source design, sharing insights from his journey, and giving us a glimpse into how research can evolve into like scalable neuromorphic hardware solutions. We'll also like thank Erastus for joining as a co-host and supporting today's session, and the Open Neuromorphic community for continuing to foster collaboration and innovation in this existing space. For all the audience out there, if you found today's session inspiring, we encourage you to like get involved. You can participate in the NVM Power-Up Design Contest, or you can contribute to open source toolchain, or even like hosting your own workshop or talk. You can find all the links and the resources on the Open Neuromorphic website, and we can continue the conversations if you have anything on our Discord community. And yeah, once again, I'd like to thank you all for being here. Keep experimenting, keep building, and we'll see you in the next session. Thank you so much.
Thank you. Thank you, everyone.